All right, so we are finally to the fundamental theorem of calculus. Very big deal. All right, part one. So we've got this special function g of x defined as an integral from a to x. Look at that. That's very different, isn't it? So the integral from a to x underneath this curve f of t dt, and the only reason we're using t's in here is because I've got an x up in the limit of integration. So g of x is actually this area. G of x is an area. Okay. So what we find, and I'll show you the proof on another piece of paper, that g prime of x is f of x. So taking the derivative of this integral, so I'm just going to write it right below. So g prime of x, the derivative of this integral, turns out to be f of x. All right, so let's go find the derivative. So sometimes I'll say it in words, sometimes I'll say d over dx, but let's just go do it. So the d over, I'll just write it in notation as well here, 1 to x of t to the fourth dt. All right, so it is x to the fourth. So you literally plug x into the function and that's it. So I'll show you the proof of what that is. It might not help for you to understand what this is what we do, but this is what we do. Okay, here we go. So here I'm taking the derivative of this integral. Oh, but wait a minute. I need to have the x up on the top limit of integration. So let's take a step and rewrite it as 2 to x. So that means I'm going to put a negative on the outside, carry everything along. And now I carry the negative along, right? Because negative with the derivative, you just carry constants along. And then I evaluate the function with the x, and that's it. All right, same for this one. Oh, what's happening here? I have an x cubed. So I'm taking the derivative of this integral. So g prime of x is the derivative of this integral. So I'm going to use my form of how to take the derivative, and I'm going to carry x cubed along. Sounds a lot like chain rule, doesn't it? So I'm putting the x cubed in everywhere there's a t, and then just like with chain rule, when I'm taking the derivative, I multiply by the derivative of that function I carried along afterwards. So this is the derivative of the x cubed. All right, so this one here, I'm going to switch the limits of integration. Put the negative on the outside, carry everything along. Oops, didn't mean to write that. T dt. All right, carry the negative. Now I'm going to evaluate the function. Put the e to the x in for the t. Then I'm going to multiply by the derivative of the function I carried along, which is e to the x. A little bit of chain rule. So that's part one. This is rarely used. Okay, this is rare. This part two, we will use all the time. So make sure you really, really know this one. Okay, and again, I'll prove it on another piece of paper. But what you do to take the integral from a to b of f of x dx, it turns out to be the antiderivative. So you know the notation for antiderivative is capital F of x. And then this a to b, so notice the integral turns into this bar. And so this bar means put in b into the antiderivative and then subtract off plugging in a. Okay, let's do it. So the integral of this function, so first I'm going to find the antiderivative of this, which is x cubed over 3 plus 5x squared over 2. And then I'm going to put this bar here, and I'm going to put the 0, and I'm going to put the 3. So what I'm going to do is I'm going to plug in x equals 3 into the function, and then I'm going to subtract off plugging in x equals 0. So if I plug in x equals 3, I get 27 over 3 plus 5 halves times 9. And then this one, when I plug in 0, I get 0. So this gives me 9 plus 45 halves. And I can just leave it like that. So this is the exact area under the curve, x squared plus 5x. So that function would just kind of look something like this. So from 0 to 3, this exact area under the curve would be this number here. Okay, let's do it again. So this is the function that I first have to find the antiderivative of. 3x squared over 2 from 1 to 3. So you put this bar, you don't write the integral sign after you've taken the antiderivative. So now be careful, I've got two things here, and I'm going to subtract off plugging in x equal 1. So first plug in the top limit of x equal 3, then subtract off plugging in the bottom limit of x equal 1. So when I plug in x equal 3, again I get 27 thirds plus 3 halves times 9. When I plug in 1, I get 1/3 plus 3 halves. So this gives me 9 plus 27 halves minus 1/3 minus 3 halves. So this is the exact area under the curve. All right, so now we have it. The short way, we don't have to do the long way of adding up an infinite number of rectangles. The long way is done. We have finally gotten to the short way of finding the integral, the definite integral.